Hello everyone, my name is Reinbigler. I'm a PhD student at Telecom SudParis, and I will present you my work entitled Toward a Metal Usage Effectiveness Metric in Data Center, a Study. So let's jump directly to the context. So currently there are one data center per day which is constructed, and thus it is paramount to be able to assess their environmental impact. So currently, lots of metrics are existing to characterize those data centers. The first category of them are here to monitor or classify them, like the power usage effectiveness, the water usage effectiveness, the material reuse effectiveness, and so on. But only a few of them are here only to assess the environmental impact. We have, for example, the green energy coefficient, the carbon usage effectiveness, and so on. But none of them actually account for raw material which are required to assemble a new data center. How do we actually quantify this raw material extraction? So there is a metric called the abiotic resource depletion, which accounts for the annual extraction rate divided by the reserve present on Earth. But it's not that metric that is usually monitored. It is more the abiotic depletion potential, which is actually the same abiotic resource depletion divided by the abiotic antimony depletion, expressed as kilogram antimony equivalent, and it is actually the equivalent of normalizing by the CO2 for CO2 equivalents. And so antimony is actually a metal that is present on Earth with a reserve of 1 gram per Earth's crust dome. So where are those materials actually used? And they're actually used in a large diversity of components like GPUs, CPUs, RAM, SSDs, network interface cards, network cables, power cables, switches, and so on. And due to this large diversity, we also require a large diversity of raw material. And the huge question is, in which quantity do we actually need each of those materials? So some studies have been conducted, like in the context of life cycle assessment efforts or recycling studies. For example, the work of Adem or Buavitsa. But the problem with those works is that usually it considers only older equipment or lower-end equipments. And this is not necessarily the ones that are used in data centers today. And concerning their composition of those actually used, they remain in general confidential. This is why in this work, we propose to model the content in copper and gold at various scales. We also propose to make a component breakdown of the computing hardware of a supercomputer, as supercomputers have more public data than an industry data center. We also estimate the copper and gold volume used in the IT equipment of the FranceA supercomputer. And finally, we define the metric we would like to monitor, the metal usage effectiveness that accounts for raw material extraction for the assembling of a data center divided by the computing power. So let's focus on our case study, which is the FranceA supercomputer. So FranceA is the first supercomputer that could reach exascale and is currently ranked second in the top 500 of the most powerful supercomputer in the world. Here you have a picture of the FranceA compute room composed of 74 cabinets. And in the context of this study, we focus only on the compute room and on the gold and copper content, even though lots of other materials should be followed at some point. So let's have a look at what is inside a cabinet. So in the back of the cabinet, what we can see is a set of switches with the associated cables. Then in the front of the cabinet, we can see the power supply unit in the middle, the power distribution unit, and a set of compute blades. Inside the compute blades, you have two compute nodes with a CPU, a RAM, a SSD, a super intermediate voltage converter, a set of GPUs, and a network interface card. Now that we know which components are inside the compute room, we can start to model the estimation of copper and gold. So let's start at the fine grain scale, which is the micro scale, and it focuses on what is happening inside the chip. And actually, inside the chip, there is a high copper content, which is located in the interconnections. So first we have horizontal interconnections, which can be wires or redistribution layers. We have an example of those two at the bottom. And we can estimate the copper content by considering the geometrical shape of a wire or redistribution layer. So it's expressed as the width multiplied by the length multiplied by the plating thickness. In a newer generation of packages, we also saw the willingness to superimpose several chips one on top of the other in order to reduce the interconnection length and thus the latency. And so that's why there are now lots of vertical interconnection, which can be made thanks to solder balls and bumps, CO pillars, or through silicon vias on the right. And so to estimate their copper content, we again consider their geometrical shape, the plating thickness. And it leads us to the volume estimation, and this can be found in the paper in more details. So now that we know what is happening inside the chip, let's take a step further and consider what is happening at the scale of the package or inside the compute blade. So inside the compute blade, we have printed circuit boards. So they are here to supply power or make interconnections among the different components. And so we can see a set of traces with a set of pads, which are usually made out of gold because we need high performance interconnections. PCB can be seen as a multi-layer cake where we have at the extremities outer copper layers and inside a set of inner copper layers of a different thickness. And actually we just reproduce the same pattern, which is a copper layer followed by a prepreg layer followed by a copper layer followed by a core layer and followed by a copper layer again, and we just reproduce it as many times as we have layers. And so to estimate the volume here, we just consider the size of the PCB card multiplied by the thickness of each copper layers, and for the gold we quantify the number of connections, we multiply it by the surface of each pad and by the thickness. And in our case, as we didn't have any information about the surface of a pad, we consider a pad of 1 millimeter squared. So if we apply it to the FranceA supercomputer with the MAD Instinct MI 250X, we supposed that we had a PCB with 8 layers with specific thickness of copper, and thanks to that we found that 31% of the GPU weight were made out of copper. And if we consider studies on PCB recycling, we found that 10 to 30% of the weight is made out of copper, which is in the same order of magnitude as our results. And this is the same for the switch PCB, the RAM PCB, the network interface card PCB, and the NVMe PCB. So now let's jump to the other mesoscale component, which are connectors. So connectors can be modeled as having a female and a male connector, which can be sometimes the same. The female connector is usually interconnected to an underlying PCB or elements via a set of pads. And we have that the male and female connector have can link to one to each other thanks to contact surfaces or contact pads. And so in this case, usually it's made out of gold because the goal is to have high performance connections. And so to estimate the volume, we need to have a number of pads that are used, the surface of a pad, and the thickness of the gold plating. And so if we want to apply it to the FranceA supercomputer, what we can see is that there are actually a large diversity of connectors. We have M2 connectors, the Open Accelerator module for GPUs, the PCI Express 4, the RDIMM DDR4 for the socket SP3 for the CPU, and the Examax and QSF PDD connectors for the network. And so if we focus on the male connector of the QSF PDD, we see that It has several patterns of paths that are repeated, and there are 3 different patterns, each of them with a specific surface that we can estimate based on the specification of this specific connector. And we have a plating thickness, which can lead us to the estimation of the gold volume. Now, let's focus on packages, which actually are the result of the aggregation of all the previously presented models. But what is important is to actually be able to identify which the exact reference of each of the components inside the blade. So here, for example, we have the MAD EPIC Trento for the CPU, 64 GB of DDR4 RAM for the CPU. We had also NVMEs of about 2 terabytes. The GPUs are AMD Instinct MI 250X as a GPU. And for the network interface card, they used the HPE Slingshot and network interface card. And so if we apply it to the supercomputer with the previous model, we could estimate both gold and copper content. And we will focus on 2 different examples. So first, let's focus on what we estimated for the RAM. So in this case, if we consider a RAM module of about 30 grams, we have that the weight of copper is equivalent to 30% of the total weight, and the one of the gold represents 0.08%. According to recycling data, the weight of copper should be between 19 and 70%, and the one of gold between 0.10 and 0.13%. So in this case, we remain in the same order of magnitude. Now let's focus on what the total of a wall node. So to do so, we considered the ATEM data on a server containing 2 CPUs, SSDs, and hard disk drives. And what they found is that it contains 1.5 kilograms of copper and almost 1 gram of gold, which is actually in our case, we measured actually the half for the copper and the double for the gold. So we still remain in the same order of magnitude, but we can explain the difference in copper by saying we didn't account for the cooling material, which has a huge amount of copper. And concerning the gold, we have 2 potential explanations. The first one is that we considered high performance equipment, meaning it requires more gold interconnections to have higher performance. And we also have here compute nodes that contains 4 GPUs, whereas on the other case, it has non-GPUs, which can lead to higher gold content. So now that we considered everything at the scale of the blade, let's take again a step back and consider what remains to be estimated in order to make the supercomputer work. And to do so, we need to consider what is happening inside cables and bus bars. So in FranceA, they use a specific set of cables. Like here, you have an example of a cable assembly. Here you have an example of the DAC copper cables. Here, power supplies cables. And what they have in common is that they all have a set of wires in there made out of copper. And so to estimate the volume of copper of cable, we just need to estimate the number of wires, their cross-section, and their length. Usually cross-section in this case are estimated using the American wire gauge. And we can also extend this formula to the case of bus bars by just adapting the cross-section as being rectangular instead of circular. So let's have a look at how are the different components linked via those cables. So let's focus first on the slingshot cables, meaning network cables. So here we need first to connect the different nodes to switches to be able to after that connect every node all together. So this first connection is called L0 cable, and it's made out of cable assembly. Then to make possible the communication between the different nodes inside the compute cabinet, we need to have L1 cables, which will connect one switch to another. And because we have a dragonfly topology where we have groups of 32 switches fully connected, we have that one switch will be connected to the 31 other switches of the same cabinet. And this is how it looks in reality. And now, to have a full dragonfly topology, we need to interconnect the different groups all together. And so to do so, it's made via L2 cable, which are made out of optical fiber, which contains mainly silicon, which is not the focus in this study. And now, considering the number of cables, their length, their cross-section, we can estimate the copper content. So now let's focus on the power supply. So here we have first the interruptible power supply, which is linked to the dual source transformers, which itself feeds the cabinet bus bars, that provides power to a power distribution unit and itself to the power supply units. Then this power supplies unit provides power to the blades bus bars that itself supplies power to all the switches and their associated nodes. So considering that the previously sequence of cables and that the interruptible power supplies are not always the closest as possible to the cabinet bus bars. Here we have an example of one located 17 meters away. We can estimate the copper content that is actually far from being negligible. Now that we have all equipment necessary to make the supercomputer work, we can now present and define the metric we propose to monitor, which is the metal usage effectiveness, which is expressed as the ADP divided by the computing power in petaflops. You may wonder, what is an ADP for a supercomputer? So actually, it's the sum of the ADP of each elements inside the supercomputer multiplied by the weight of these elements, like gold or copper. And now, if we focus on the results of FranceA, we can see that for the copper, the weight is estimated to be 20 kilograms in total, and it comes mainly from the compute, due to the fact that it is there that we need very high performance interconnections. Then we have that the copper weight comes mainly from the power, which is due to the fact that the cables are quite long with a quite high cross-section. And finally, the ADP comes mainly from the compute again, because the ADP from the gold is way higher than the one from the copper. So at the end, thanks to all those weights estimated, we can measure MUE of 0.34 for the whole supercomputer. And so here what is now possible to do is to monitor how modification in frontier components will influence this metric. And so the lower, the better. So let's discuss a bit our results. So first, we acknowledge that we had to make absorption to estimate volumes due to the lack of information publicly available. We focused only on the compute hardware, but it would be very important to add cooling infrastructure, physical infrastructure, storage and management nodes inside the model to have a complete view. Then we are focused only on gold and copper elements, but we should focus on any material that is a resource constraint and used to build and assemble data centers. In this study, we also focused on high performance equipments, and this work may need some adaptation to apply to any type of data center. We also didn't account for material recycling inside the ADP estimation, and it should be added to have a more accurate value. And now let's conclude on what we presented. We actually noticed that there are no metrics to account for data centers' material consumption, and this is why we proposed a new metric called the metal usage effectiveness, which is the ADP divided by the computing power. We proposed a set of models using a multi-scale approach to estimate both copper and gold using only publicly available data. And we applied it to the FranceA supercomputer computer room. We obtained a metal weights that are in the same order of magnitude than what we can find in the literature. And this work should be extended to cooling, storage, and monitoring infrastructures, as well as to other material required. And finally, this work would benefit from collaboration with manufacturers by having an MUE computed inside the company, or by having them providing more information about the composition of their different hardware component in order to have a better estimation of the metal usage effectiveness. And I thank you for your attention.